Hi, my name is Oren Mangoubi. Today I'll be talking about convex optimization with unbounded non-convex oracles. So I'm from EPFL and a postdoc at EPFL, and this is joint work with my advisor, Nisheeth Vishnoi. So I'll start off by talking about the problem setting that we're considering, as well as the motivation for this problem setting. Then I'll talk about some of the issues with more traditional approaches to this problem setting. Then I'll talk about how some of these issues can be solved by using simulated annealing. And finally, I'll talk about how to bound the running time of our algorithm. So in our problem setting, we're given a noisy approximation f hat. So we have access to a noisy approximation f hat for a convex function f with global minimizer x star. And the function is defined on a convex set k. So our goal is to find an approximate minimizer x hat such that f of x hat minus f of x star is less than some error epsilon. So some applications to this problem setting are, one, if you want to optimize convex function f, however, it's computationally expensive to evaluate this convex function. So instead, you want to evaluate a cheaper approximation f hat to this function. So another application is if instead you want to optimize a non-convex function, which is nevertheless known to be close to a convex function. Okay, so in order to analyze algorithms for this general problem setting, we need to assume some model on the error of this approximation f hat. So in other words, which we call the noise. So the simplest noise model we can assume is the additive noise model. So in this case, the error f of f hat of x minus f of x is assumed to be uniformly bounded by some constant beta. So this situation was first analyzed by Applegate and Canaan. Okay, so another model that we can consider for the noise is the multiplicative noise model. So in this case, the error f hat of x minus f of x is bounded by f of x minus f of x star times some constant alpha. So we call this constant alpha the multiplicative noise level. And beta is the additive noise level. So in particular, for the multiplicative noise model, the noise increases as you move away. So the error increases as you move away from the global minimizer. So in this talk, we'll be considering a generalization of these two models, which is the additive and multiplicative noise model, where you have your error for f hat is a sum of an additive noise term and a multiplicative noise term. So the question we want to answer is it possible to find an approximate global minimum in polynomial time when you have this non-uniform additive multiplicative noise? Okay, so now I'll talk about some prior work as well as the result that we prove. So for the special case where you only have additive noise, so this was analyzed by Applegate and Canaan for the grid walk algorithm, and more recently by Zhang et al. For stochastic gradient Langevin dynamics. So they proved that if your additive noise level beta is bounded by epsilon over d, then it's possible to minimize the convex function f to this accuracy epsilon in polynomial time. So it turns out that this upper bound on the noise level is actually necessary to get polynomial running time bounds. So this complexity result was proven by Bloom and Rivest. Okay, so all of this was for additive noise. So what about multiplicative noise? So Bologna et al. Analyzed a version of the multiplicative noise case. So they did this for the special case where the function f, the convex function f, is assumed to be strongly convex. So in this case, they were able to show that you can get get an approximate optimization for this function f under this version of multiplicative noise in polynomial time. Okay, so for the result that we show, we assume that the function f is convex, but not necessarily strongly convex, and defined on a convex constraint set k. And we also assume that we have access to a noisy oracle f hat for this function, which has both additive and multiplicative noise terms, where the additive noise is bounded above by epsilon over d, and the multiplicative noise is bounded by 1 over d. And so under these assumptions, we show that it's possible to find an approximate minimizer x hat such that f of x hat minus fx star is less than this error epsilon in polynomial time. So so the running time is polynomial in both in the dimension as well as various smoothness parameters for the function f. So in particular, the assumptions we made about f was that it was convex, but we did not need to make strong convexity assumptions. Okay, so the algorithm that we used is based on the Langevin dynamics Markov chain. So the idea is that if we run this Markov chain after many steps, we reach point x, which is distributed according to the Gibbs distribution e to the minus f hat of x over t, where t is a temperature parameter that's associated with the Markov chain. So the question is, if we want to get an efficient optimization algorithm using this Markov chain, how should we choose the temperature? So if we use a fixed hot temperature, then the Markov chain will quickly, so we're running this Markov chain on the approximate function f hat. And if we use a hot temperature, then the Markov chain will quickly escape the local minima, but it will not concentrate near the global minimum. On the other hand, if you run this Markov chain at a fixed cold temperature, it will reach minimum values of f hat, but it will approach minimum values of f hat, but it will get stuck in the local minima and take a long time to escape them. So to solve this problem, we use the simulated annealing method, which means that we start by running our Markov chain at a high temperature, and then so that it can escape the local minima, but then we gradually decrease the temperature so that it eventually concentrates near the global minimum. Okay, so how do we prove our running time bounds? So the strategy that we use, so here we're running the Markov chain on the non-convex function f hat, which approximates the convex function f. And the strategy that we use is we divide the space into the level sets of the convex function f. And we show that as we decrease the temperature of the Markov chain, the Markov chain concentrates in smaller and smaller level sets of f, and therefore converges to the global minimum of f. So the idea is that since at each step we decrease the temperature, so you'd think that so normally you need a higher temperature to escape larger local minima, but the point is as the function concentrates in the smaller level sets, the points in the Markov chain are closer to the global minimizer, which means that the level of multiplicative noise becomes smaller as you decrease the temperature, which allows the Markov chain to quickly hit the next level set, even though you've decreased the temperature, since the noise level goes down as you approach the global minimizer. And to bound the hitting time, we use the Cheeger constant for these level sets. Okay, so in particular, this level set approach that we use is what allows us to show polynomial running time bounds without assuming strong convexity on the function. Okay, so in summary, we combined Langevin dynamics with the simulated annealing method. We also introduced this combined additive multiplicative noise model. So under this model, we proved that our algorithm finds an approximate global minimizer in polynomial time. So one question we still have is that for what levels alpha of multiplicative noise is it possible to achieve polynomial running times? So another question is, let's say the function f, so not the approximate function, but the actual function you want to optimize, is a non-convex function. But you want to find a local minimum of this non-convex function f given access to a noisy oracle with non-uniform noise, such as multiplicative noise. So in this case, is it possible to obtain polynomial running times bounds for finding local minima of non-convex functions? Okay. Thank you.
Great. So maybe a quick question for Oren, if there is any. And if not, let's thank everybody in the session for very interesting talks.